The second objective in the lesson 3.5 is to linearize and analyze data. They go into this description of linearizing data and why we're learning about it and how it works. But in a nutshell, what we're doing is we're learning how the calculator linearizes data to help you find the curve of best fit. So basically, it doesn't matter what you give it. You can give it exponential data, you can give it logarithmic data, you can give it power model data, and points of data that would model exponential growth, or that would model a quadratic growth, or cubic, or it could be a square root graph for all that matters. All those families of graphs that we have, we can feed it that, but what the calculator is going to do is it's going to do an algorithm that's going to linearize the data and help find the curve of best fit. So we can take data that looks like this, which is exponential, looks exponential, or it could even look like it's a power model. It could be a quadratic model, and honestly it could be a cubic model. We might not be seeing all the data, and it could come down here and it could curve back down. We're not seeing as much of the data as we probably would need to get an accurate picture. But the calculator has an algorithm in there that takes this data, it transforms the values, and what they're doing, they're showing you a log transformation. So the original x values stay the same. What they do is they transform the y values by taking all the logarithms of all these y values. We're going to do this all in the calculator, so you don't have to sweat about, oh, I got to punch all those in. It's pretty easy when you look at how we're going to approach this on the calculator. So it's going to take the data that looks like an exponential growth model, and if we do the appropriate transformation, it should linearize the data, and what we're going to see is these points really cluster around a straight path. And then in Core 2, what you learned, and what we did quite a bit of work with, was learning how the calculator found the line of best fit. And that used the sum of the least squared errors line. So what it would do is it take your data and it would say how far is it from the line, and it would square those differences, and it would minimize that distance. And so it's the sum of the squared errors. It's the least sum of the squared errors line that fits that curve. And I hope that connects a little bit with you, because we did spend some time with that and showing you how a calculator finds a line of best fit for linear data. So in essence, what the engineers have done with this calculator is they're saying, we got a really good algorithm for linearizing or finding the line of best fit for linear data. So let's use some mathematics here to take every scatter plot that we have, linearize the data, and find the curve of best fit. So that's what it's going to do. The other thing that was really beneficial in our other curriculum, if we had the pre-calc book from last year, it made a really good case for why linearizing data was important for data analysis. One of the things that's really difficult when you look at this original data set, the original data set is increasing at an increasing rate. Well, we have several models that show this type of growth rate. Like I said, this could represent a power model, such as x squared, or it could be x cubed, it could be a fourth degree. So there are several different models that could fit this data. Another model that could fit this data well is an exponential model. And that's where the rub was. Whenever we're looking at different models, exponential models and power models and quadratic models, those variety, they all kind of look alike. So we wanted a way to differentiate between what would be the best model that would represent this data. So what we looked at in the old book was how we can transform this data most effectively to tell us what kind of model it was. Is it a power model? Is it an exponential model? Is it a quadratic model, or so on? So that process was called linearizing the data. Well, we're going to summarize some of the key concepts here, and then I'm going to break, and then I'm going to come back and do some examples here for you. But the key concept is, basically, if we're going to transform or linearize the data, what we want to do is, kind of the concept here is do the inverse. If it's a quadratic function, our main or our dominant term is squared. So if we want to undo squaring to semi-linearize that data, we would graph the order pairs of x square root of y. So let me describe this. You're going to get a set of original data. You're going to have x values in list 1 in your calculator. You're going to have your y values of your original data set in list 2. In list 3 of your calculator, what you're going to do is you're going to transform the data by taking the square root of your original y values, and that's going to be placed in list 3. Then you graph your list 1, list 3, your original x values and your transformed y values on your calculator screen, and it should linearize the data if it was a quadratic model or even a squared term model. Okay, so if it's an exponential model, we're thinking about the common thing would be, what is the inverse of an exponential? And that would be logarithm. So what you're seeing here is a transformed data. If we think it's an exponential model, if the data indicates it's increasing at an increasing rate, and we think the context of the problem says that lends itself to an exponential model, we might apply an x natural log of y. And this should linearize your data. The ones that we haven't done a lot with, and I haven't had a lot of experience with, are logarithmic functions, but if we have a log function, we know that the growth rate is increasing at a decreasing rate. So it goes fast at first and then slow at the end. We know what those graphs look like. So if we get a scatter plot that looks like that, then we're probably going to have to run this type of transformation, and this doesn't quite fit with the context I gave you where you want to do the inverse of a logarithmic. You'd think you'd want to exponentiate. So this kind of breaks away from that rule a little bit, but that rule works well for many different examples, and I'll come back and show you again. But if you think it's a logarithmic model, then you take the natural log of x and y. So you transform the x values but not the y, then you graph your new x values and your old y values and see if it linearizes. And the final one that they're mentioning here is a power function. Power functions are the family of functions that look like this: y equals a times x to the b. If we think we have a power model or a power function model by our data, then what we can do to try to linearize it is take the natural log of your original x's and the natural log of your original y's, and that should linearize your data. Okay, so here's where I want to go back to the study tip: linearizing data modeled by other polynomial functions. Here's where this rule where if it's quadratic, you square root. If it's exponential, you take the natural log. But if it's a cube, if you have a cubic function, then we want to take the cube root of your y values to linearize it. In the same vein, the quartic function, which is to the fourth power of the dominant term, we want to do the inverse, which would be the fourth root. So there is this association between taking the inverse function to help linearize the data. That scheme breaks down a little bit with your logarithmic and power functions, so there's some little bit of exception to that rule. The next study tip here is just on some vocabulary or some terminology. Whenever you hear a semi-log transformation, that means we transform just either the x or the y values, but not both. So here's where my cursor is, x natural log of y. We're transforming just the y values, not the x's. So semi means it's a partial log and it's a partial original data set or linear set. On the other one, it's a natural log of x comma y. We have this partial. Semi means part way. It's halfway here. It's halfway a log transformation, the other half is not. So we're taking the log of the x values but not the y's, and that's if it was a log function that we suspected. We also have log-log data transformations, and that log-log transformations is what you're going to apply anytime you think a power model is the best fit for the data. And I don't want to make this real confusing, but if you get it in context, if they tell you what the nature of the problem is, if we get real-world applications, a lot of times that tips the hands of the deck or of our hand, so that we know kind of what we're looking for. There's going to be some context clues to tell us what model is going to fit best. Anytime we're working with gravity, we know that's a squared function, so we're looking at a power model. A lot of times we're working with populations. Populations typically will grow at an exponential rate, but sometimes a power. So we'll have some things that will kind of lend itself to giving you an upper hand, and so you kind of know what kind of model it'll be. So the log-log transformation basically means you did a log of the x and a log of the y, and you did that for power functions if you want to linearize those. So at this point I want to stop in the part of that video, let you kind of have a little piece of that mystery here, and then we're going to go back in and I'm going to show you example number 5 and how to actually carry out this linearization process. Use your calculator appropriately. It's going to be a lot of changing of screens and windows and transformation of data, but it's maybe time consuming, but it's not difficult. So I'm going to stop this and I'm going to pick up the example in the next video then.